Assalamu alaikum and welcome to another class about the control of volatile organic compounds. And in this class, we will talk about some of the technologies that are used to control VOCs in the effluent of industries coming out of these stacks, for example. So in the last videos, we covered the carbon adsorption, the first one. And in this class, we'll cover oxidation, condensation, and bioreaction. So oxidation could be done or could be explained as another word for combustion, because combustion would be the very easy way to think about oxidation. So basically the VOCs, if you combust them, and the VOCs, they are actually hydrocarbons. The VOC, which is CXHYOZ plus O2 will give NCO2 plus MH2O. And this is your regular combustion reaction. So when we are combusting VOCs, which this is the VOC, by the way, so if you don't understand, this is the VOC. So the VOC will disappear, will react, and instead we will have CO2 and H2O. How do we do that? We can do that by several ways. One of them is flares, other is thermal oxidizer and catalytic oxidizers, and I will tell you the difference between each one of them in a minute. There are also different there are boilers, there are other turbines. So there are a lot of other ways of doing combustion, but these are the three most common. Let me put it this way. So a flare, I'm pretty sure that you've seen it either on the side of a highway, you've seen it in a movie, but it's actually this very large column that has some flame on top and it keeps burning. Have you ever seen that before? I'm pretty sure you did. So this flare, why do we keep burning stuff in the air? Why do you think that is? Because we're burning the VOC, or we have a stream of gas somewhere that we need to get rid of. So instead of just releasing it into the air, we are burning it. But we cannot just burn it like with a match. We collect it, put it in one column, and then we make sure that we have at least a little bit of controlled burning. And this controlled burning is done by a flare. So you can see here that there is first a flare stack. That's the stack where you're combining all the gas together and it's going up. And then there is a steam distribution ring. That's where you distribute steam all around. Steam injection point, that's where the steam is going. Waste retention ring, and then a pilot assembly. What is this pilot assembly? Have you ever seen a gas heater at home? Or water heater, gas water heater? Or only you have electric? Electric. Have you seen the gas ones? The gas ones, you always, if you see them, they actually turn on demand. So when you have hot water, they start to work. They basically have a flame to heat the water while it's going. If you turn off the hot water, they close. They are a little bit different concept than the electric one. A flare works exactly the same way. So you turn it on, it's like a lighter. You turn it on, then it will have the flame, and as long as you are feeding the flame with gas, something that can burn, the flame will keep continuing, right? So similar to the lighter, you always need a first spark, or you need a flame that's always there. Similarly to the gas water heater at home, you will always, if you look inside, you will always see a very small flame that keeps going regardless if it's on or off. Why? So that whenever there is a need, this flame will be the spark that starts the whole the whole heating. And this is what we call the pilot. So the flame, exactly. So it's a small flame that's working all the time. So once you turn it on, then this flame is directed towards the gas, and then it's a big fire, basically. Okay? So this tells you that the flare works on demand. So it's not doesn't have to be working all the time. So it works whenever you need it. However, the pilot is running all the time. Thermal oxidizer. Before we move from the flare, there is just one point that I wanted to point out. Now, methane is natural gas. Methane is good, but sometimes we don't have the capacity to collect all of it. Okay? And while we are doing exploration, for example, so you try to look for oil and gas, let's say there is big pressure of methane. Now, this methane is being vented to the atmosphere. Should we let it vent or should we burn it? Why? You said burn it. Why should we burn it? It will react with other elements. It's in the right path, but that's not the correct answer. What is methane? But what type of pollutant it is? Methane is part of the class of greenhouse gases. Greenhouse gas, which is bad for global warming. So if we have methane out, CH4, and we burn it, will give me so what class of pollutants is CO2? Greenhouse gas as well. So now I'm burning one greenhouse gas, the CH4, to get another greenhouse gas, which is the CO2. Is that a good thing or a bad thing? So 1 mole of methane gives how many moles of CO2? 1 to 1. So because 1C, 1C, right? So 1 mole of methane will give 1 mole of CO2. So the question becomes, even if they are both greenhouse gas, which one is more worse to the environment, to the global climate change? Methane is 28 times worse than CO2. That's why we need to burn it. If we don't burn it, we are actually increasing the impact by 28 times. Although CO2 is not good, but at least it's 28 times better than the business as usual case. So that's another use of flares. Make sense? Or the thermal oxidizer is a refractory brink line chamber with one or more oil gas burners. So it's basically a big oven. You know the oven that you have at home? And the oven, but much higher temperatures and much bigger. So refractory line means that it has lining that to keep the heat from outside, so you don't get everybody burnt around it. And it uses oil or gas to burn everything inside. So it looks something like that. It will have inlets for the gas, and then it will have a flame inside, and then it will have outlets for the gas. So the gas will be going around. This is like, if you look at it, so it will be like a ring like this. where this is the inlet. So the gas is going all the way from inside, and in the middle, there is the flame inside. So the gas will go and then find its way with the flame and then gets burnt while it's doing that. And then the gas without VOCs will be coming out of the exit. The temperatures, we get there around 1300 to 1800 Fahrenheit. And the residence time is about 0.3 to 0.5 seconds. Any questions? So the thermal oxidizer is really good and works in a very high efficiency. However, it has one problem. Can you think about what is the problem when we have this kind of... Do we need to add anything else? Is it like this, or do we have any other input? Let me ask you the question in a different way. How do you make sure that your temperature remains between 1300 and 1800? No, but what if it goes down to 1200? What will you do? You need this temperature to destroy the VOCs, right? But what if you cannot get that? What if you get 900? What if you get 800? So as an engineer, we are engineers. We engineer things. We make them work the way we want them to work. That's really our job in life. How do you make sure that the temperature reaches the target? Oil and gas. So you need to supplement the fuel that's going in. So you are burning VOCs, which has a heat value, but maybe it's enough. Maybe it's not enough. You always need an external fuel source. So you're actually paying money or wasting resource, right? Which is the oil and gas. Imagine the gasoline that you put in your car. You are just using it just to burn the VOCs, not to move the car, not to do anything useful. There is no product that's coming out of it. But you're actually paying money and depleting one of the resources just to get rid of the VOCs. So a good thing to do is to reduce the amount of external fuel that you need, right? This is, if you ask me how can you improve this process? Use less oil and gas. We can, but then I think it will be very inefficient because you need to a lot of power to convert this to go up to temperatures of 1000 Celsius, right? You are taking much lower temperatures and you want to... Even if it's 100, still 1000 is very far from it. So the idea here, now let me try to use another color. Not sure how to do that. Okay, so now let's say the oil and the gas, it's either oil or gas. It's not oil and gas, right? So you choose, everyone is designed for a specific fuel, like a car. You cannot just put any fuel in the car. So let's say the fuel is coming here. What happened when I put the fuel and also, you remember also in this ring, the pollutant is coming in. What temperature are they getting in? Room temperature, most likely, right? Most likely, as long as it's not the process itself, the industrial process is hot, It's usually a gas stream coming at room temperature and coming in, and also your natural gas is coming at room temperature and getting in. So what happens in this zone here? What is the temperature? It's very low, right? Because it just came in. Remember, it's coming at room temperature. While it's moving, the temperatures are increasing. Now, temperatures are much more. Temperatures are really high. This means that this part of the reactor, or the thermal oxidizer, this part is not really very efficient because it operates at lower temperatures than you need to burn. So you're losing space. So a way to make this more efficient is actually to heat the gases as they are getting inside the oxidizer. So that instead of this to be that big, I reduce this to this much or that much. Make sense a little bit? So now I can use more space, more volume of my oxidizer. That means I use less fuel because they are all interconnected. And this is the whole idea behind using this recuperative thermal oxidizer. So since I already have a very high temperature inside the oxidizer, very smart guy thought, if I have the gas that is running in a tube to go inside the oxidizer, if I run this tube inside the oxidizer without touching, so the tube itself is inside, but the gas is inside, so the gas does not really touch the oxidizer, I am heating the gas inside the tubes. And then when I introduce it to the oxidizer, it's already now at a much higher temperature. So I am actually getting use of the waste energy that's being developed inside the oxidizer to heat the influent gas. So I'm introducing it at a higher temperature, so I am lowering the total energy consumption. Make sense? So let's look here. This is your solvent. This is your VOC in. Now, what happens in this VOC in? You see, it goes here in these tubes. And it keeps going around. Now, this is really hot. Inside the tubes, there is hot air coming from the oxidizer. And the gas keeps going around it. So the gas itself keeps heating up. So if here the temperature is equal to 20, here it's equal to 200, here it's maybe equal to 600. While it's going, it keeps increasing the temperature. And then it is going here to next to the flame. You see the flame? The red one is the flame. So you are, instead of putting it next to the flame, you're putting it from the other side and let it make sure that it passes through a lot of heat to increase its temperature and then reintroduce it. This makes sure that you do use much less energy. Any questions about the recuperative thermal oxidizer? Another type of oxidizer is called regenerative thermal oxidizer. It's also a very smart design that plays among the same thing. So in the regenerative thermal oxidizer, we use ceramics that can maintain the heat for a very long time. What basically the whole idea is to heat it by the effluent or the outlet of the oxidizer, and then it keeps the temperature. I pass through it, I switch, and I pass through it the inlet while it's hot. So now the inlet already is warming up when it touches the ceramics. So it's like heating something and then passing air through it, so the air itself, and then going to another cycle for another unit where I'm heating it and passing air, and I keep going back and forth. So it's usually much more than 2 units. They are 6, 8, 10 units, where some of them are heating, some of them are being used to heat the infant. And again, this makes sure that I use less energy. Just food for thought. Do you know how water desalination is being done right now in UAE? When we get water out of the sea that has salt. Do you know how we remove the salt? Mesh nets. There are. Okay. Okay, the idea is okay. So there are 2 technologies. One of them is reverse osmosis. I think that's what you are referring to. It's not really, it's a membrane, it's not a net. So it's a membrane that can only pass the water and rejects the salt. Okay, that's not what I'm talking about now in this example. But the other example is called thermal distillation, where I use the heat to evaporate some of the water, to leave some salt behind, and then get water. That's more or less the idea. So in the thermal evaporators, I actually use the excess heat that comes out of energy generation. That's the current practice in UAE. So every power plant, the one that burns coal, burns oil, burns gas to make electricity, which actually is the exactly same idea as an oxidizer. It's just a big oxidizer. It produces heat while it's doing this. So I take the extra heat and use it, try to evaporate the water to reject the salt out and get clean water. Most of our water currently is done by this method. So you see how everything is related? And the heat, the excess heat, I use it for water. Smart. All right. All right. So process heaters and boilers. Boilers must operate at 40 to 100% of full load. Contaminated gas stream flow rate should be small portion of total, nothing corrosive or that causes deposits. So very similar idea to, again, the gas heater at home. The gas heater at home, I don't really know how to draw it, but it's just flames, 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 and the water is passing through this steel pipes where it's being heated by these flames, and it's when it's a lot of fire, basically, it increases temperature too much. Catalytic oxidizer is another oxidizer that uses some chemistry to reduce your energy requirements. So what really happens is that, yes, we need to reach 1300 to 1600 Fahrenheit to make sure we destruct all the VOCs. So some chemist who's smart at one point, it's not one, but he found out that there is something called catalyst. And you've all learned about catalysts. What do catalysts do? Do you remember? They accelerate, but that's not exactly what they do. Yeah, that's the end result, that they accelerate the reaction. Remember something about activation energy? They lower the activation energy requirement. So basically, if this is temperature, and this is reaction, so you always need to reach this, what you call activation energy, activation temperature. So you always need to reach this point in order for the reaction to proceed. What the catalyst does is it reduces your activation energy. So instead of having to go all this much, you can actually happen here. So instead of E1, E node, you get E1, which is lower. So meaning that the reaction of the VOC, the oxidation of the VOC with oxygen, can be done at temperatures lower than 1300 if you have the right catalyst. And this is what a catalytic oxidizer. Catalytic oxidizer has some chemical catalysts, chemical materials that lower the activation energy of the VOC reaction, oxidation reaction, and make it happen at a lower temperature. This temperature could be 700 to 900. That means I need less fuel. That means less cost, right? So then it's another way of saving. You can see that the whole idea here is to get rid of the VOCs with the least costs possible. So let's think about the catalysts. Can I use them forever? Unfortunately, good things don't happen to every day. It's too good to be true. So catalysts have a time, and then you have to change them or reactivate them. You have to take them, and because it's a chemical reaction. So the catalyst material include noble metal oxides such as platinum, palladium, rhodium. So as you see, they are usually not the metals that are expensive, and they are not your regular metals that you use every day. And there is a base metal oxides such as vanadium, titanium, and manganese. This is how a catalyst would look like. They use it in this shape, trying to increase the surface area available, because again, similar to the carbon, if you remember from the last class, the more surface area you have, the more reaction you can get. So our idea is to have the catalyst with the most surface area possible. This is how it looks as sheets. Temperatures, about 100 Fahrenheit above catalyst light-off temperature. The typical input temperature is from 500 to 600 Fahrenheit, typical outlet 700 to 900, and the maximum outlet temperature is 1100 to 1200. So within your oxidizer, we can calculate something called space velocity, which is Q over BV, which is the bed volume. And so basically this is very easy, that's V is equal to Q over A. That you know from high school physics. It's exactly the same rule. Typically, it's 30 to 40,000 per hour for noble metals, and it's 10,000 to 15,000 per hour for metal bases. However, catalyst has problems. They are fouling, meaning that they get spoiled. They get poisoned. Poisoned is not like they are consumed, but poison means that there is some material that they get exposed to that inactivates what they do. So then they are not good anymore in their actual job. Masking, meaning that they take them out of service, so they are still good, they are not poisoned, but they are out of service. Or thermal aging, because they are exposed to very high temperature, and after some time they age, and we need to replace them. So the catalysts, before we go to the next slide, the catalysts usually are proprietary. Companies that actually do manufacture these catalysts, they don't tell what it is made of. They actually rent it, usually rent it to the industries. So if you have a factory, I will come as a vendor for catalysts and I will give you a closed box and I will put it, and then I will come after some time, remove the box and put another box. You have no idea what's in the box, how it works, but you rent the control from me, because there is a lot of money that's involved in the chemistry of catalysts. Big industry. So with this, we will stop here for the first video, and then the next video we'll be talking about condensation.